Guys, how's it going? Let me continue. On page 192 or 200. The compilers currently allow a pointer to be assigned to an integer to a pointer, and a pointer to a pointer of another type. The assignment is a pure copy operation with no conversion. This usage is non-portable. It may produce pointers which cause addressing exceptions when used. However, it is guaranteed that assignment of the constant 0 to a pointer will produce a new pointer distinguishable from a pointer to any object. 7.15 Comma operator. A pair of expressions separated by a comma is evaluated left to right, and the value of the left expression is discarded. The type and value of the result are the type and value of the right operand. This operator groups left to right in contexts where comma is given a special meaning, for example, in a list of actual arguments to functions. 7.1 In the list of initializers. 8.6 The comma operator, as described in this section, can only appear in parentheses. For example, like this has 3 arguments, the second of which has the value 5. 8 Declarations. Declarations are used to specify the interpretation which C gives to each identifier. They don't necessarily reserve storage associated with the identifier. Declarations have the form: the declarators in the declarator list contain the identifiers being declared. The specifiers consist of a sequence of type and storage class specifiers. The list must be self-consistent in a way described below. 8.1 Storage class specifiers. The SC specifiers are like this. The type-diff specifier does not reserve storage and is called a storage class specifier. Only for syntactic convenience, it is discussed in 8.8. The meanings of the various storage classes were discussed in Chapter 4. The auto-static and register declarations are reserved as definitions in that they cause an appropriate amount of storage to be reserved. In the external case, there must be an external definition. Chapter 10. For the given identifiers somewhere outside the function in which they are declared, a register declaration is best thought of as an auto-declaration, together with a hint to the compiler that the variables declared will be heavily used. Only the first few such declarations are effective. Moreover, only variables of certain types will be stored in registers. On the PDP-11, they are int, char, or pointer. One other restriction applies to register variables. The address of operator ampersand cannot be applied to them. Smaller, faster programs can be expected if register declarations are used appropriately, but future improvements in code generation may render them unnecessary. At most, one SC specifier may be given in a declaration. If the SC specifier is missing from a declaration, it is taken to be auto inside a function, extern outside. Exception functions are never automatic. 8.2 Type Specifiers. The type specifiers are like this. The words long, short, and unsigned may be thought of as adjectives. The following combinations are acceptable. The meaning of the last is the same as double. Otherwise, at most one type specifier may be given in a declaration. If the type specifier is missing from a declaration, it is taken to be int. Specifiers for structures in unions are discussed in Chapter 8.5. Declarations with type-diff names are discussed in 8.8. 8.3 Declarators. The declarator list appearing in a declaration is a comma-separated sequence of declarators, each of which may have an initializer. Initializers are discussed in Chapter 8.6. The specifiers in the declaration indicate the type and storage class of the objects to which the declarators refer. The declarators have a syntax. The grouping is the same as in expressions. 8.4 Meaning of declarators. Each declarator is taken to be an assertion that when a construction of the same form as the declarator appears in an expression, it yields an object of the indicated type and storage class. Each declarator contains exactly one identifier. It is this identifier that is declared. If an adorned identifier appears as a declarator, then it has the type indicated by the specifier heading and declaration. A declarator in parentheses is identical to the adorned declarator, but the binding of complex declarators may be altered by parentheses. See the examples below. Now imagine a declaration where T is a type specifier, like int, etc., and D1 is a declarator. Suppose this declaration makes the identifier have type like this is empty if D1 is just a plain identifier, so that the type of lowercase x in an int x is just int. Then if D1 has the form asterisk uppercase D, the type of the contained identifier is. If D1 has the form, then the contained identifier has the type. If D1 has a form like this, or then the contained identifier has type like this. In the first case of the constant expression is an expression whose value is determinable at compile time, and whose type is int. Parentheses constant expressions are defined precisely in Chapter 14. When several array of specifications are adjacent, a multi-dimensional array is created. The constant expressions which specify the bounds of the arrays may be missing only for the first member of the sequence. This addition is useful when the array is external and the actual definition which allocated storage is given elsewhere. The first constant expression may also be emptied when the declarator is followed by initialization. In this case, the size is calculated from the number of initial elements supplied. An array may be constructed from one of the basic types, from a pointer, from a structure or union, or from another array. To generate a multi-dimensional array, not all the possibilities allowed by the syntax above are actually permitted. The restrictions are as follows. Functions may not return arrays, structures, unions or functions, although they may return pointers to such things. There are no arrays of functions, although there may be arrays of pointers to functions. Likewise, a structure or union may not contain a function, but it may contain a pointer to a function. As an example, the declaration declares an integer I, a pointer IP to an integer, a function f returning an integer, a function FIP returning a pointer to an integer, and a pointer PFI to a function which returns an integer. It is especially useful to compare the last two. The binding of asterisk FIP parentheses is asterisk parentheses FIP parentheses, so that the declaration suggests and the same construction in an expression requires the calling of a function FIP and then using indirections through the parenthesis pointer result to yield an integer. In the declarator parentheses asterisk PFI parentheses, the extra parentheses are necessary, as they are also in an expression, to indicate that indirection through a pointer to a function yields a function, which is then called. It returns an integer. Here's another example. Declares an array of float numbers and an array of pointers to float numbers. Finally, declares a static three-dimensional array of integers with rank 3 multiply 5 multiply 7. In complete detail, X3D is an array of 3 items. Each item is an array of 5 arrays. Each of the later arrays is an array of 7 integers. Any of the expressions X3D, X3D, bracket I, X3D, bracket I, bracket J, X3D, bracket I, bracket J, bracket K may reasonably appear in an expression. The first 3 have type array, the last has type int. 8.5 Structure and Union Declarations. A structure is an object consisting of a sequence of named members. Each member may have any type. A union is an object which may, at a given time, contain any one of several members. Structure and union specifiers have the same form. The struct dec list is a sequence of declarations for the members of the structure or union. In the usual case, a struct declarator is just a declarator for a member of a structure or union. A structure member may also consist of a specified number of bits. Such a member is also called a field. It is named is set from the field name by a column. Within a structure, the objects declared have addresses which increase as their declarations are read left to right. Each long field member of a structure begins on an addressing boundary appropriate to its type. Therefore, there may be named holes in a structure. Field members are packed into machine integers. They do not straddle words. A field which does not fit into the space remaining in a word is put into the next word. No field may be wider than a word. Fields are assigned right to left on the PDP-11, left to right on other machines. A struct declarator with no declarator, only a column and a width, indicates an unnamed field useful for padding to conform to external imposed layouts. In a special case, an unnamed field with an width of 0 specifies alignment of the next field at a word boundary. The next field presumably is a field, not an ordinary structure member, because in the later case, the alignment would have been automatic. The language does not restrict the types of things that are declared as fields, but implementations are not required to support any but integer fields. Moreover, even int fields may be considered to be assigned. On the PDP-11, fields are not assigned and have only integer values. In all implementations, there are no arrays of fields, and the address of operator ampersand may not be applied to them. So that there are no pointers to fields. A union may be thought of as a structure of all whose members begin at offset 0 and whose size is sufficient to contain any of its members. At most, one of the members can be stored in a union at any time. A structure or union specifier of the second form, that is one of this, declares the identifier to be the structure tag or union tag of the structure specified by the list. A subsequent declaration may then use the third form of specifier, one of like this. Structure tags allow definition of self-referential structures. They also permit the long part of the declaration to be given once and used several times. It is illegal to declare a structure or union which contains an instance of itself, but a structure or union may contain a pointer to an instance of itself. The names of members and tags may be the same as ordinary variables. However, names of tags and members must be mutually distinct. Two structures may share a common initial sequence of members. That is, the same member may appear in two different structures if it has the same type in both and if all previous members are the same in both. Actually, the compiler checks only that a name in two different structures has the same type and offset in both. But if preceding members differ, the construction is non-portable. A simple example of a structured declaration is which contains an array of 20 characters, an integer, and 2 pointers to similar structures. Once the declaration has been given, the declaration declares S to be a structure of the given sort and SP to be a pointer to a structure of the given sort. With these declarations, the expression refers to the count field of the structure to which SP points, refers to the left subtree pointer of the structure S, and refers to the first character of the word member of the right subtree of S. 8.6 Initialization. A declarator may specify an initial value for the identifier being declared. The initializer is preceded by equal and consists of an expression or a list of values nested in braces. Wait a minute, hang on. Okay. Continue. All the expressions in an initializer for a static or external variable must be constant expressions, which are described in 15, or expressions which reduce to the address of a previously declared variable, possibly offset by a constant expression. Automatic or register variables may be initialized by arbitrary expressions involving constants, and previously declared variables and functions. Static and external variables which are not initialized are guaranteed to start off as 0. Automatic and register variables which are not initialized are guaranteed to start off as garbage. When an initializer applies to a scalar, a pointer, or an object of arithmetic type, it consists of a single expression, perhaps in braces. The initial value of the object is taken from the expression. The same conversions as for assignment are performed. When the declared variable is an aggregate, a structure, or an array, then the initializers consists of a brace enclosed, comma-separated list of initializers for the members of the aggregate. Read in increasing subscript or member order. If the aggregate contains sub-aggregates, this rule applies recursively to the members of the aggregate. If there are fewer initializers in the list than there are members of the aggregate, then the aggregate is padded with zeros. It is not permitted to initialize unions or automatic aggregates. Braces may be listed as follows. If the initializer begins with a left brace, then the succeeding comma-separated list of initializers initializes the members of the aggregate. It is erroneous for there to be more initializers than members. If, however, the initializer does not begin with a left brace, then only enough elements from the list are taken into account for the members of the aggregate. Any remaining members are left to initialize the next member of the aggregate of which the current aggregate is a part. A final abbreviation allows a char array to be initialized by a string. In this case, successive characters of the string initialize the members of the array. For example, like this, Declarators and initializes X as a one-dimensional array which has 3 members. Since no size was specified and there are 3 initializers, like this is a completely breaked initialization. 1, 3, and 5 initialize the first row of the array y break it 0, namely y break it 0 break it 0. Likewise, the next 2 lines initializer y and y2. The initializer ends earlier, and therefore y3 is initialized with 0. Precisely the same effect could have been achieved by like this. The initializer for y begins with the left brace, but that for y does not. Therefore, 3 elements from the list are used. Likewise, the next 3 are taken successively for y1 and y2. Also, like this goes. Initializes the first column of y regarded as a 2-dimensional array and leaves the rest 0. Finally, shows a character array whose members are initialized with a string. 8.7 Type names in two contexts to specify type conversions explicitly by means of a cast and as an argument of size of. It is desired to supply the name of a data type. This is accomplished using a type name, which in essence is a declaration for an object of that type which omits the name of the object. To avoid ambiguity in the construction, hang on. The abstract declarator is required to be non-empty. Under this restriction, it is possible to identify uniquely the location in the abstract declarator where the identifier would appear if the construction were a declarator in the declaration. The named type is then the same as the type of the hypothetical is the type of the hypothetical identifier. For example, name respectively the types integer, pointer to integer, array of 3 pointers to integers, pointer to an array of 3 integers, function, returning pointer to integer, and pointer to function returning an integer. 8.8 Type div. Declarations whose storage class in typediff do not define storage, but instead define identifiers which can be used later as if they were typed keywords, naming fundamental or derived types. Within the scope of a declaration involving typediff, each identifier appearing as part of any declarator therein become syntactically equivalent to the type keyword, naming the type associated with the identifier in the way described in 8.4. For example, after the instructions are all legal declarations, the type of distance is int, that of metric is pointer to int, and that of z is a specified structure. zp is a pointer to such a structure. Typediff does not introduce brand new types, only synonyms for types which could be specified in another way. Thus, in the example above, distance is considered to have exactly the same type as any other int object. 9. Statements, except as indicated, statements are executed in sequence. 9.1 Expression statement. Most statements are expression statements which have the form Usually expression statements are assignments of function calls. 9.2 compound statement or block, so that several statements can be used where one is expected. The compound statement also an equivalently called block. It's provided it it's provided like this. If any of the identifiers in the declaration list were previously declared, and the outer declaration is pushed down for the duration of the block, after which it resumes its force. Any initializations of auto or register variables are performed each time the block is entered at the top. It is currently possible, but a bad practice to transfer into a block. In that case, the initializations are not performed. Initializations of static variables are performed only once when the program begins execution inside a block. External declarations do not reserve storage, so initialization is not permitted. 9.3 Conditional Statement. The two forms of the conditional statement are if both cases the expression is evaluated and if it is non-zero. The first substatement is executed. In the second case, the second substatement is executed if the expression is zero. As usual, the else ambiguity as usual, the else ambiguity is resolved by connecting an else with the last encountered else less if. 9.4 While statement. The while statement has the form like this. The substatement is executed repeatedly. The substatement is executed repeatedly so long as the value of the expression remains non-zero. The test takes place before each execution of the statement. 9.5 Do statement. The do statement has the form like this. The substatement is executed repeatedly until the value of the expression becomes zero. The test takes place after each execution of the statement. 9.6 for statement. The fourth statement has a form like this. This statement is equivalent to like this. Thus, the first expressions specifies initialization for the loop. The second specifies a test made before each iterations. Such that the loop is excited when the expression becomes zero. The third expression often specifies an incrementation which is performed after each iteration. Any of all of the expressions may be dropped. A missing expression too makes the implied while clause equivalent to while parenthesis 1. Other missing expressions are simply dropped from the expansion above. 9.7 Switch statement. The switch statement causes control to be transferred to one of several statements depending on the value of an expression. It has the form Like this, the usual arithmetic conversion is performed on the expression, but the result must be int. A statement is typically compound. Any statement within the statement may be labeled with one or more case prefix as follows, where the constant expression must be int. No two of the case constants in the same switch may have the same value. Constant expressions are precisely defined in Chapter 15. They may also be at most one statement prefix of the form. When the switch statement is executed, when the switch statement is executed, when the switch statement is executed, its expression is evaluated and compared with each case constant. If one of the case constants is equal to the value of the expression, control is passed to the statement following the matched case prefix. If no case constant matches the expression, and if there is a default prefix, control passes to the prefixed statement. If no case matches, and if there is no default, then none of the statements in the switch is executed. Case and default prefixes in themselves do not alter the flow of control, which continues unimpeded across such prefixes. To exit from a switch, see break in 9.8. Usually the statement that is the subject of a switch is compound. Declarations may appear at the head of this statement, but initializations of automatic or register variables are ineffective. 9.8 Break statement. The break statement causes termination of the smallest enclosing while, do, for, or switch statement. Control passes to the statement following the terminated statement. 9.9 Continue statement. The statement continue causes control to pass to the loop continuation portion of the smallest enclosing while, do, or for statement. That is to the end of the loop. More precisely, in each of the statements, continue is equivalent to go to counting. Following the counting, continue is a new statement. 9.13 9.10 Return statement. A function returns to its caller by means of the return statement, which has one of the forms. In the first case, the returned value is undefined. In the second case, the value of the expression is returned to the caller of the function. If required, the expression is converted as if by assignment to the type of the return to the type of the function in which it appears. Following of the end of a function is equivalent to a return with no returned value. 9.11 Go to statement. Control may be transferred unconditionally by means of the statement. Identifier must be a label. 9.12 Located in the current function. 9.12 Labeled statement. Any statement may be preceded by label prefixes of the form, which serve to declare the identifier as a label. The only use of a label is as a target of a go-to. The scope of a label is the current function, excluding any subblocks in which the same identifier has been redeclared. See Chapter 11. 9.13 Null statement. The null statement has a form semicolon. A null statement is useful to carry a label just before the braces of a compound statement, or to supply a new body to a looping statement such as while. 10. External definitions. A C program consists of a sequence of external definitions. An external definition declares an identifier to have storage class external by default or perhaps static, and a specified type specifier may also be empty, in which case the type is taken to be int. The scope of external definitions persists to the end of the file in which they are declared, just as the effect of declarations persists to the end of a block. The syntax of external definitions is the same as that of all declarations, except that only at this level may be code for functions be given. 10.1 External function definitions. Function definitions have the form like this. The only SC specifiers allowed among the Type Specifiers are external or static. See 11.2 for the distinction between them. A function declarator is similar to a declarator for a function returning, except that it lists the formal parameters of the function being defined. The identifiers in the parameter list, only those identifiers may be declared in the declaration list. Any identifiers whose type is not given are taken to be int. The only storage class which may be specified in register. If it is specified, the corresponding actual parameter will be copied, if possible, into a register at the outset of the function. A simple example of a complete function definition is: herein is the type specifier max parenthesis a comma b comma c is the function declarator int a comma b comma c is the declaration list for the formal parameters, is the block giving the code for the statement. C converts all float actual parameters to double, so formal parameters declared full float have their declaration adjusted to read double. Also, since a reference to an array in any context, in particular as any actual parameter, is taken to mean a pointer to the first element of the array, declarations of formal parameters declared array of are adjusted to read pointer to. Finally, because structures, unions, and functions cannot be passed to a function, it is useless to declare a formal parameter to be a structure, union, or function. Pointers to such objects are, of course, permitted. 10.2 External data definitions. An external data definition has the form: the storage class of such data may be external, which is the default, or static, but no auto or register. 11. Scope rules. A C program need not all be compiled at the same time. The source text of the program may be kept in several files, and precompiled routines may be loaded from libraries. Communication among the functions of a program may be carried out both through explicit calls and through manipulation of the external data. Therefore, there are two kinds of scope to consider. First, what might be called the Lexicoscope of an identifier, which is essentially the region of a program during which it may be used without drawing undefined identifier diagnostics, and second, the scope associated with external identifiers, which is characterized by the rule that references to the same external identifier and identifier are references to the same object. 11.1 Lexicoscope. The lexicoscope of identifiers declared in external definitions persists from the definitions through the end of the source file in which they appear. The lexicoscope of identifiers which are formal parameters persist through the function with which they are associated. The lexicoscope of identifiers declared at the head of blocks persists until the end of the block. The lexicoscope of labels is the whole of the function in which they appear, because all references to the same external identifier refers to the same objects. Seeing 11.2 The compiler rejects all declarations of the same external identifier for capability. In effect, their scope is increased to the whole file in which they appear. In all cases, however, if an identifier is explicitly declared at the head of a block, including the block constituting a function, any declaration of that identifier outside the block is suspended until the end of the block. Remember also 8.5 that identifiers associated with ordinary variables on the one hand and those associated with structure and union members and text on the other form two disjoint classes which do not conflict. Members and text follow the same scope rules as other identifiers. Type div names are in the same class as ordinary identifiers. They may be redeclared in inner blocks, but an explicit type must be given in the inner declaration. The int must be present in the second declaration, or it would be taken to be a declaration with no declarators and type distance. 11.2 Scope of externals. If a function refers to an identifier declared to be external, then somewhere among the files or libraries constituting the complete program, there must be an external definition for the identifier. All functions in a given program which refer to the same external identifier refer to the same object, so care must be taken that the type and size specified in the definition are compatible with those specified by each function which references the data. The appearance of the external keyword in an external definition indicates that storage for the identifiers being declared will be allocated in another file. Thus, in a multi-file program, an external data definition without the external specifier must appear in exactly one of the files. Any other files which wish to give an external definition for the identifier must include the external in the definition. The identifier can be initialized only in the declaration where storage is allocated. Identifiers declared static at the top level in external definitions are not visible in other files. Functions may be declared static. 12. Compiler control lines. The C compiler contains a preprocessor keyboard of macro substitution, conditional completion, and inclusion of name files. Lines beginning with hash communicated with this preprocessor. These lines have syntax independent of the rest of the language. They may appear anywhere and have effect which less, independent of scope, until the end of the source program file. 12.1 Token replacement. A compiler control line of the form. Note, no trailing semicolon. causes the preprocessor to replace subsequent instances of the identifier with the given string of tokens, a line of the form. Where there is no space between the first identifier and the parenthesis is a marker of definition with arguments. Subsequent instances of the first identifier followed by a parenthesis, a sequence of tokens delimited by commas and a are replaced by the token string in the definition. Each occurrence of an identifier mentioned in the formal parameter list of the definition is replaced by the corresponding token string from that call. The actual arguments in the call are token strings separated by commas. However, commas in quoted strings are protected by parentheses do not separate arguments. The number of formal and actual parameters must be the same. Text inside a string or a character constant is not subject to replacement. In both forms, the replacement string is rescanned for more defined identifiers. In both forms, a long definition may be continued on another line by writing backslash at the end of the line to be continued. This facility is most valuable for definition of manifest constants. As in, a control line of the form causes the identifier's preprocessor definition to be forgotten. 12.2 File inclusion. A compiler control line of the form causes the replacement of that line by the entire contents of the file name. The named file is searched for first in the directory of the original source file, and then in a sense of standard places. Alternatively, a control line of the form searches only the standard places and not the directory of the source file. 12.3 Conditional completion. A compiler control line of the form checks whether the constant expression evaluated is to non-zero. A control line of the form checks whether the identifier is currently defined in the preprocessor, that is, whether it has been the subject of a hash-defined control line. A control line of the form checks whether the identifier is currently undefined in the preprocessor. All three forms are followed by an arbitrary number of lines, possibly containing a control line, and then by a control line. If the checked condition is true, then any lines between hash else and hash endif are ignored. If the checked condition is false, then any lines between the test and hash else or lacking and hash else and the hash endif are ignored. These constructions may be nested. 12.4 Line control. For the benefit of other preprocessors which generate C programs, a line of the form causes the compiler to believe, for purposes of error diagnostics, that the line number of the next source line is given by the constant and the current input file is named by the identifier. The identifier is absent. The remembered file name does not change. 13. Implicit declarations. It is not always necessary to specify both the storage class and the type of identifiers in a declaration. The storage class is supplied by the context in external definitions and in declarations of formal parameters and structure members. In a declaration inside a function, if a storage class but no type is given, the identifier is assumed to be int. If a type but no storage class is indicated, the identifier is assumed to be auto. An expression to be the later rule is made for functions. Since auto functions are meaningless, C being incapable of compiling code into the stack, if the type of an identifier is function returning, it is implicitly declared to be external. In an expression, an identifier followed by and not already declared is contextually declared to be function returning int. 14. Types revisited. This section summarizes the operations which can be performed on objects of certain types. 14.1 Structures and unions. There are only two things that can be done with a structure or union. Name one of its members by means of the point operator, or take its address by unary ampersand. Other operations such as assigning from or to it, or passing it as a parameter, draw an error message in the future. Is it expected that these operations, but no necessarily others, will be allowed? 7.1 says that Chapter 7.1 says that in direct or indirect structure reference with point or arrow, the name on the right must be a member of the structure named or pointed to by the expression on the left to allow an escape from the typing rules. This restriction is not firmly enforced by the compiler. In fact, any F value is allowed before point, and that F value is then assumed to have the form of the structure of which the name on the right is a member. Also, the expression before a arrow is required only to be a pointer to or an integer. If a pointer it is assumed to point to a structure of which the name on the right is a member. If an integer, it is taken to be the absolute address in machine storage units of the appropriate structure. So constructions are non-portable. 14.2 Functions. There are only two things that can be done with a function: call it or take its address. If the name of a function appears in an expression not in the function name position of a call, a pointer to the function is generated. Thus, to pass one function to another, one may say, not may, my, one might say, the definition of G might read. Notice that F must be declared explicitly in the calling routine, since its appearance in G was not followed by. 14.3 Arrays, pointers, and subscripting. Every time an identifier of array type appears in an expression, it is converted into a pointer to the first member of the array. Because of this conversion, arrays are not L values. By definition, the subscript operator predicate is interpreted in such a way that E1 is identical to asterisk Okay, because of the conversion rules which apply to plus, if E1 is an array and E2 an integer, then E1 bracket E2 refers to the E2's member of E1. Therefore, despite its asymmetric appearance, subscripting is a commutative operation. A consistent rule is followed in the case of multi-dimensional arrays. If E is an n-dimensional array of rank, then E appearing in an expression is converted to a pointer to n minus 1 dimensional array with rank. If the asterisk operator, either explicitly or implicitly as a result of subscripting, is applied to this pointer, the result is the pointed to n-1 dimensional array, which itself is immediately converted into a pointer. For example, consider like this case. Here x is a 3 multiplied 5 array of integers. When x appears in an expression, it is converted to a pointer to the first of 3 5-membered arrays of integers. In the expression x bracket I, which is equivalent to asterisk parenthesis x plus I, x is first converted to a pointer as described, then I is converted to the type of x, which involves multiplying I by the length of object to which the pointer points, namely 5 integer objects. Results are added and is interaction applied to yield an array of 5 integers, which in turn is converted to a pointer to the first of the integers. If there is another subscript, the same argument applies again. This time, the result is an integer. It follows from all this that arrays in C are sorted row-wise, lest the subscript varies faceted, and that the first subscript in the declaration helps determining the amount of storage consumed by an array, but plays no other part in subscripting calculations. 14.4 Explicit pointer conversions. Certain conversions involving pointers are permitted but have implementation-dependent aspects. They are all specified by means of an explicit type conversion operator. Chapter 7.2 and 8.7. A pointer may be converted to any of the integer types larger enough to hold it, where an int or long is required as machine dependent. The mapping function is also machine dependent, but is intended to be unsurprising to those who know the addressing structure of the machine. Details for some particular machines are given below. An object of integer type may be explicitly converted to a pointer. The mapping always carries an integer converted from a pointer back to the same pointer, but is otherwise machine dependent. A pointer to one type may be converted to a pointer to another type. The resulting pointer may cause addressing exceptions upon use if the subject pointer does not refer to an object suitably aligned in storage. It is guaranteed that a pointer to an object of a given size may be converted to a pointer to an object of a smaller size and back again without change. For example, a storage allocation routine may accept a size embodies of an object to allocate and return a character char pointer. It might be used in this way. A lock must ensure in a machine-dependent way that its return value is suitable for conversion to a pointer to double, then the use of the function is portable. The pointer representation on the PDP-11 corresponds to a 16-bit integer and is measured in bytes. Char have no alignment requirements. Everything else must have an even address. In the Honeywell 6000, a pointer corresponds to a 36-bit integer. The word part is in the left 18 bits, and the 2 bits that select the character in a word just to their right. Thus, character pointers are measured in units of 2 power 16 bytes. Everything else is measured in units of 2 power 18 machine words. Double quantities and aggregates Double quantities and aggregates containing them must lie on an even word address. The IBM 370 and the Interdate 8/32 are similar. On both addresses are measured in bytes. Elementary objects must be aligned on a boundary equal to their length. So pointers to short must be 0 mod 2, and int and float 0 mod 4, and to double 0 mod 8. Aggregates are aligned on the strictest boundary required by any of their continuants. 15. Constant expressions. In several places, C requires expressions which evaluate to a constant. After case is array bounds, and in initializers. In the first 2 cases, the expression can involve only integer constants, character constants, and size of expressions, possibly connected by the binary operators, or by the unary operators, or by the ternary operator. Question. Parentheses can be used for grouping, but not for function calls. More latitude is permitted for initializers. Besides constant expressions, as discussed above, one can also apply the unary ampersand operator to external or static objects, and to external or static arrays subscript with a constant expression. The unary ampersand can also be applied implicitly by appearance of an subscripted arrays and functions. The basic rule is that initializers must evaluate either to a constant or to the address of a previously declared external or static object plus or minus a constant. 16. Portability considerations. Certain parts of C are inherently machine dependent. The following list of potential trouble spots is not meant to be all inclusive, but to point out the main ones. Purely hardware issues like word size and the properties of floating point, arithmetic, and integer division have proven in practice to be not much of a problem. One faces of the hardware are reflected in differing the implementations. Some of these, particularly sign extension, converting a negative character into a negative integer, and the order in which bytes are placed in a word are a nuisance that must be carefully watched. Most of the others are only minor problems. The number of register variables that can actually be placed in registers varies from machine to machine, as does the set of valid types. Nonetheless, the compilers all do things properly for their own machine. Excess or invalid register declarations are ignored. Some difficulties arise only when dubious coding practices are used. It is exceedingly unwise to write programs that depend on any of these properties. The order of evaluation of function arguments is not specified by the language. It is right to left on the PDP-11, left to right on the others. The order in which side effects take place is also unspecified, since character constants are really objects of type int. Multi-character character constants are permitted. The specific implementation is very machine dependent, however, because the order in which characters are assigned to a word varies from one machine to another. Fields are assigned to words and characters to integers right to left on the PDP-11 and left to right to other machines. These differences are invisible to isolated programs which do not indulge in type punning. For example, by converting an int pointer to a char pointer and expecting the pointed to storage, but must be accounted for when conforming to externally imposed storage layouts. The language accepted by the various compilers differs in minor details. Most notably, the current PDP-11 compiler will not initialize structures containing bit fields and does not accept a few assignment operators in certain contexts where the value of the assignment is used. 17. Anachronism. Analogous anachronism. Anachronisms. What is this word? Anachronism. Since C is an evolving language, certain obsolete constructions may be found in other programs. Although most versions of the compiler support such anachronisms, ultimately they will disappear, leaving only a portability problem behind. Earlier versions of C used the form equal OP instead of OP equal for assignment operators. This leads to ambiguities typified by x equal -1, which actually decrements x since the equal and the minus are adjacent, but which might easily be intended to assign -1 to x. The syntax of initializers has changed. Previously, the equal sign that introduces an initializer was not present. So instead of int, one used like this. The change was made because the initialization resembles a function declaration closely enough to confuse the compilers. 18. Syntax summary. This summary of C syntax is intended more for adding comprehension than as an exact statement of the language. 8.1 Expressions. The basic expressions are like this. Primary L value. The primary expression operators have highest priority and group left to right. The unary operators have priority below the primary operators but higher than any binary operator, and group right to left. Binary operators and the conditional operator all grouped left to right and have priority decreasing as indicated. Assignment operators all have the same priority and all group right to left. The comma operator has the lowest priority and groups left to right. 18.2 Declarations like this. In other words, 80.3 Statements, this component. 18.4 External definitions, like this word. 18.5 Preprocessor. So many preprocessor. Okay, got it. Index. This doesn't have to read. Okay. Hey guys. It is not easy. And finally, we come to the end. Okay. There's a lot of things I have to do because I find some words, a few words that I don't know what they mean. So I have to check it out and I have to figure it out. See you the next time. Okay. Goodbye.